Hello all, welcome to the next lecture of network analysis and synthesis. In the previous lecture, we have introduced what is meant by synthesis, and we have discussed the basic concept of network functions. So in this lecture, let us see what is the condition that is necessary to be satisfied by the network function in order to do the network synthesis. So as we discussed, network synthesis cannot be done for every network function. Okay, so there should be some conditions that need to be satisfied. Okay, so before this, so if you take any network function, so which is generally a Laplace transform of some quantity, that is, let's say, voltage or current or right, whatever, so to another quantity, right, Laplace transform of another quantity. So let us write in general the h of s, we can write it as a ratio of p of s to q of s, where p of s is one polynomial in s, so it's like a power s power n plus b into s power n minus 1 plus and so on up to s power 0 divided by, okay, let's say q of s is another one, so let's say we have c into s power m plus d into s power m minus 1 plus and so on up to s power 0. So just an example. So in this case, right, p of s is one polynomial in s and q of s is another polynomial in s. Generally, our network function will be of this form. Okay. So because this is a polynomial of nth order, so it will have n roots. Similarly, this denominator polynomial is having m roots. Okay. So the roots are nothing but the values of s where p of s will become 0, and here the roots are nothing but the values of s where q of s is becoming equal to 0. Okay, so in case of a network function, right, the values of s where the numerator is becoming 0, that is where the transfer function network function itself is becoming 0. Okay, so these points of s are referred to as the zeros of the network function. Okay, zeros of the network function. Okay, next, the values of s where, right, q of s is becoming 0, that means h of s becomes equal to infinity, where h of s becomes equal to infinity. So these values of s where the network function or transfer function is becoming infinity are called as the poles of the network function. So for every network function, there will be some zeros where the value of the network function is becoming 0, right, and there are poles where the value of network function becomes infinity or the denominator is becoming 0. Okay, so these are poles and these are zeros. Okay, and the plot of the poles and zeros, which we call it as the pole zero plot, right, is a very important information because it characterizes the network function. Okay, so it is a very important characteristic quantity for any network function. Okay, so this is a very important thing. Okay, yeah, based on this pole zero plot, we can determine so many inferences from it, so which we don't need here. Okay, so this is just a brief right, thing about what are the poles and what are the zeros of the network function. Okay, yeah, right. Now let us go into the the next topic. So we have covered what is network function and what are the properties, okay, of the network function, what is poles and what are zeros. Yeah, next, the condition for network synthesis. So as I said, so network synthesis cannot be done by taking every network function. So if a network synthesis has to be performed, then that network function has to satisfy certain conditions. Okay, so right, what are the conditions? Okay, in general terms, right, and we can synthesize the networks which can be or which are both stable and causal in nature. So the two conditions that need to be satisfied are stability and causality. Okay, causality. So right, stability and causality. If we can only synthesize the networks which are stable and causal in nature. If they are not stable and if they are not causal, then we cannot synthesize them. Okay, so this is in general in terms of system point of view or from a network point of view. But here, from the function point of view, that is from the network function, because we are given with the input which is network function, right? We don't know what is the network, so we cannot check without the network. How can we check whether it is stable or causal? It's not possible. Okay, so in terms of network function, in order to satisfy these two conditions, okay, if these two conditions are satisfied, okay, right, so in terms of network function, to check whether these two conditions are satisfied or not, we do, right, we do checking for a thing called as positive real function. Okay, so if, right, the condition is, if we want to synthesize a network function, then the necessary and sufficient condition is the network function should be a PRF. It should be a positive real function. Okay, if this condition is satisfied, if the network function satisfies this positive, right, if the network function is a positive real function, then we can do the synthesis of the network. Okay, so simple condition, we have to check whether the given network function is a positive real function or not. If it is a positive real function, then we can synthesize the network, otherwise we cannot do the synthesis. Okay, so the thing is, if the network function is a positive real function, then it is representing a, right, a stable and a causal system, okay, a stable and causal network. Okay, yeah, so the necessary and sufficient condition for a network for performing network synthesis is, so you have to check whether the given network function is, right, causal, is a positive real function or not. Okay, yeah, so how to check it? So how can we check a network function is satisfying this condition or not? Okay, or what are the properties of the positive real functions? What are positive real functions, or what are the properties of a positive real functions? Okay, let us see. So the properties of positive real functions. Okay, or these are also the conditions that are used for checking the positive real functions. Okay, yeah, so let us say that the given network function is h of s is equal to p of s by q of s. This is our network function. Okay, yeah, so first property is, or the first condition that we have to check is, the denominator polynomial q of s must be Hurwitz polynomial, must be a Hurwitz polynomial. This is the first condition that has to be satisfied. Okay, the denominator polynomial of the network function, that is q of s, must be a Hurwitz polynomial. Okay, so what is meant by, again, what is a Hurwitz polynomial? Okay, or how can we check whether it is Hurwitz or not? Okay, so Hurwitz polynomial is a special polynomial. Okay, so how to check it? Okay, for right, if I take q of s as a Hurwitz polynomial, we can call this as a Hurwitz polynomial if it satisfies three conditions. Okay, three things. Okay, first thing is, all the coefficients of the polynomial must be positive. Okay, so q of s is generally, right, generally it is a polynomial, right, a polynomial in s. Okay, let us say it is like this: a into s power n, okay, a1 or an into s power n plus an minus 1 into s power n minus 1 plus an minus 2 into s power n minus 2 plus and so on, right, a1 into s1 plus a0 into s power 0 or a0. Okay, so this is the denominator polynomial q of s. Okay, so in this right, denominator polynomial, right, all the coefficients, that is an minus 1, an minus 2, a1 and a0, all of them must be positive in nature. Okay, so all of them must be positive values, then only it is, right, then only the first condition is satisfied. Okay, so first thing is, all the coefficients must be, right, real. Okay, real. Second thing, right, positive. Second thing is, right, okay, so all the terms of s must be present Okay, from the highest to the lowest powers must be present from highest power to lowest power. Okay, lowest power, right? So this indicates that, for example, right, if the highest power of s in a given polynomial is 4, let us say, so we have s power 4 as the highest degree, the lowest degree will be s power 0, right? So in between this, so right, s cube, s square, s power 1, right? So right, this condition says that, right, if the from the highest degree to the lowest degree, all the powers should exist. That means the coefficients of these, of all the powers, should not be 0. Any coefficient should not be, cannot be 0, right? Any random coefficient, right, let's say a p is should not be 0. Okay, so from starting from the highest power to the lowest power, right, all the coefficients must exist. Okay, so that is a second condition, right? Here there is one small exemption for this. So what is the exemption is, okay, right, there is a possibility that, okay, there is a possibility that all the even terms, okay, or all the odd terms, can, right, can miss. Let's say, right, so I have okay, highest power as s power 4. Then my, if my polynomial has only even powers, s power 4, s square, s power 0, okay, that means all the odd powers of s are missing. Okay, similarly, if let's say the highest power is s power 5, okay, then s power 5, s cube, and s power 1, okay, they exist. S power 4, s square, and s power 0 are missing. Okay, in that case, these two can also be satisfying this condition. That means all the even powers or all the odd powers can miss. Okay, that's an exemption to this condition. Okay, yeah. The third condition, which is the very important one. Now, if I take this polynomial, right, and split this polynomial into two parts, one containing the even powers, okay, one containing the even powers, other containing the odd powers. Okay, one containing the even powers and other containing the odd powers. So I am splitting this polynomial into two parts. Let's say one even polynomial, odd polynomial. And then, okay, after splitting, if I divide this even to odd, right, okay, and perform the successive division, okay, that means successive division means whatever the remainder that comes here, this will now become the divisor and this will go here. Okay, so like this. So again, same thing. Okay, so this comes here. Okay, like this. So if I perform the successive division, okay, so first thing what I do, so I will split this polynomial into two parts, even part and odd part. Okay, then by using either even to odd or odd to even, perform the successive divisions. Okay, then all the coefficients, right, all the coefficients that I get should be positive, okay. So if there is even one negative quotient, the quotients that I am going to get in the case of successive division should all be positive. Okay, if there is any, right, quotient which is negative, then we can say that this polynomial is, right, not a Hurwitz polynomial. Okay, so, right, the first condition in checking whether the given network function is a positive real function or not is that the first condition is the denominator must be a Hurwitz polynomial. So what is a Hurwitz polynomial? So any polynomial can be called as a Hurwitz polynomial if it satisfies the three conditions. What are the three conditions? First thing is all the coefficients of the polynomial must be positive. Second, all the terms of s must exist starting from the highest power to the lowest power. And third, right, if you split the polynomial into even and odd terms and perform the successive division of even to odd or odd to even, anything. Okay, so if I go on doing the successive division, then all the quotients I obtain should be positive. Okay, so if any polynomial satisfies these three conditions, then we can say that that polynomial is a Hurwitz polynomial. Okay, yeah. So just one example, I will take one example for checking whether this Hurwitz, for explaining this Hurwitz polynomial. Yeah. So let us take one polynomial q of s is equal to s power 4 plus 3s square plus 6s 3s cube plus 6s square plus 2s plus 9. Okay, let us take, this is the polynomial we have. Okay, so this is the polynomial, right? Now let us check whether this polynomial is Hurwitz or not. Okay, let us test whether this polynomial is Hurwitz or not. Okay, yeah, first condition, so all the quotient coefficients must be positive. Yes, they are all satisfying. So condition 1 is satisfied, all the coefficients are positive. Second condition, we need to check all the terms are present or not. Yes, s power 4 is there, s cube is there, s square is there, s power 1 is there, s power 0 is there. So all the coefficients are existing. So second condition is also satisfied. Okay. Third condition we are going to check, right? So what is that? So we need to split this into two polynomials, odd powers of s as one polynomial, even powers of s as another polynomial. So what are the even powers? Highest power is even, right? So even powers, s power 4, 6s square plus 9. Okay, so this is the even polynomial. And then odd polynomial. What is odd polynomial? 3s cube plus 2s. Okay, now because I have even polynomial as the highest power, so I am going to divide, okay, even by odd. Okay, right? So let us do that. Okay, yeah, so 3s cube plus 2s, okay, will be my divisor. S power 4, 6s square plus 9. So we need to divide in such a way that we cancel out the first term. So if I want to cancel out the first term, here I have got 3s power cube, 3s cube, and here I have s power 4. So I need to divide this by or multiply this by s power 3. Sorry, s by 3. So when I do that, so s cube into s will become s power 4 and 3 gets cancelled. Okay, so s power 4 plus, okay, 2s into s becomes s square and this will become 2 by 3 s square. Okay, plus 9. Oh, sorry. Okay, yeah, so this will remain as it is, only two terms. Okay, right, when I subtract them, s power 4 gets cancelled. So 6s square minus 2 by 3 s square plus 9. Okay, so 6s square, okay, so 18, 3 6 are 18 minus 2, that is 16 by 3. So we can write this as 16 by 3 s square, okay, plus 9. Okay, now this will be my reminder. This reminder, whatever I've got, this will be now my, okay, divisor. Okay, so dividend we have to take this. So this 3s cube plus 2s. Okay, yeah. Now again the same concept, we need to take out this first term. Okay, so for getting, we need to get 3s cube. Okay, so first thing is I have to multiply with s. Okay, right. So 16 has to go out. So 16, right? So here 3 has to go out and I need to get 3 here. So that means I need to divide it with, multiply with 9. Okay, so when I multiply with 16 by 3 into 9 by 16, 16 gets cancelled, I'll get 3s cube. Okay, yeah, so therefore this term will be 3s cube. Okay, right, plus, so this will become 9 plus 9 into 9 is 81. Okay, so 81, right, by 16 into s. So this gets cancelled. Okay, so yeah, what is this? I'm going to get 2s minus 81 by 16 into s. Okay, so 16 2 ja, right, that will become 32. 32 minus 81, so 81 minus 32 will be, right, 11, so 2, and this will be 7 minus 3 is 4, so 49. So this will become, yeah, so this whole term will become minus 49 by 16 into s. Okay, yeah. So next thing is, now right, we need to cancel out this will come here. So 16 by 3 into s square plus 9. Okay, so we need to, right, cancel out this one. So here, see, I have got a minus here. Okay, so therefore I need to multiply this with minus, okay, s, right? And what is that I need to do? I need to cancel out this 49. So I need to, right, divide it with 49. Okay, and right, I need to, in the denominator, right, I have a 16 which I need to cancel out and I have to get a numerator. So 256, So when I multiply this, and I need to get a 3 here, so therefore I have to have a 3 here. Okay, so this will give me the same result. Okay, so when I do this, 16 by 3 into s square, okay, right, will be the left out term. Okay, yeah, so this will get cancelled, this I'll get 9. Okay, right. So but see here, because right, because the point is we got a negative quotient. Okay, yeah, so here I got a negative quotient. So look at the quotients. First quotient, second quotient are positive, but the third quotient is negative. Okay, so therefore, right, because we got a negative quotient, we can stop it here. Right, we can do the further by taking 9 as the divisor. Right, okay, and this as the dividend. Right, we can perform the division until we get 0, but that's not required, because once we get even a negative quotient, one single quotient, it is going to be not a Hurwitz polynomial. Okay, so therefore we can say that this polynomial is not a Hurwitz polynomial. Okay, yeah, so I hope you have understood the process. Right, this is the process by which we can check whether the given polynomial is a Hurwitz polynomial or not. Okay, yeah, so the first condition is okay, so the denominator polynomial of the whatever the network function given, it has to be Hurwitz. Okay, so that we need to check. How we can do? We have taken the two conditions. Next, second condition is, so the second condition to be satisfied by the network function in order to call that as a positive real function. So the second condition is, so the positive real function h of s, if you take, right, so it should be, right, the real of h of s, the real part of h of s, okay, the real part of the h of s, right, okay, or you can say, yeah, we can write it in another way, right, so h of s is real, right, for every real value of s. Okay, right, for every real value of s. So if I substitute, s is generally, as I said, r plus j omega. Okay, you can write it as something like this, or a plus j omega b. Okay, so that means yeah, s is generally, right, we write it as a plus jb. It is a complex value, right? So if for example, if the imaginary part of this s is 0, right, and if s is equal to a, so if I substitute any real value of s, then the h of s, okay, then the h of s should also be real. Okay, right, అంటే నేను ఒక s value, if I substitute a real value of s, then whatever the result I'm going to get, the h of s, that should also be real. Okay, so that is a condition to be satisfied. If that condition is satisfied, we can call, right, we can get the second condition. Okay, so how to check this? So right, what is the simplest way to check, right, because we cannot do this every time. Okay, a simple condition. So in all, this condition will be satisfied if the numerator and denominator polynomials, if the numerator and denominator polynomials have only positive coefficients in them. Okay, have only positive and real coefficients in them. Okay, so if they have only positive and real coefficients in the numerator and denominator for a network function, then definitely this condition will be satisfied. That means the network function will be real if the value of s you are substituting is real. Okay, so this condition will be satisfied, right, if the numerator and denominator have only positive real functions. Okay, clear with this? So this is another very important condition, right, condition that we need to check. Okay, so that means the numerator and denominator polynomials must be having only positive real coefficients. Okay, so this is the second condition. Okay, right, now let us go to the third condition. So the third condition, right, is we have, right, the real part of h of j omega. So when I substitute, right, when I substitute s is equal to j omega, right, for every value of s which is equal to j omega, so for every value of j omega, this condition has to be satisfied. That is, when I substitute s is equal to j omega in h of s, right, and if I take the real part of this, then it should be greater than 0. That means it should be positive. Okay, so the third condition to be satisfied is the real part of h of j omega, generally, that is, which is obtained by writing s is equal to j omega. Okay, so if I substitute s is equal to j omega in my network function and take the real part of that, okay, so take the real part of that, then if that real part is greater than 0, that is, if it is a positive quantity, then the third condition is satisfied, and we call the network function as a positive real function. Okay, so right, the third condition to be checked, or the third property of the positive real function, is the real part of the h of j omega, which is obtained by substituting s is equal to j omega, right, is greater than 0. Okay, so right, every time, okay, because right, this substitution of s is equal to j omega and solving, right, all these things, okay, it's a tedious process. So we have a simplified condition for checking whether this is satisfying or not. Okay, so for that, what we do is, okay, if I take h of s, okay, so if we have, let us say, h of s is equal to p of s by q of s. Okay, p of s is polynomial in s, q of s is another polynomial. So what I do is, I'll split the p of s into, right, even and odd parts. Okay, right, p of s is splitted into two parts having even powers of s and odd powers of s, which even powers of s, I am writing it as m1 of s is nothing but the even powers in, right, p of s. Okay, and n1 of s is odd powers. Okay, so I split this numerator polynomial into two parts. One is, right, even powers of s and another is odd powers of s. Similarly, q of s is also split into two parts. Okay, so even powers of s as one part and odd powers of s as another part. Okay, so these are the two things I will do. Okay, now what I do is, okay, after doing this, then m1 of s into m2 of s, okay, minus n1 of s into n2 of s. So I calculate, right, this equal. If this is greater than 0, right, then whatever the value of condition that I get will be, right, obtained. Okay, when you substitute s is equal to j omega. Okay, yeah. So what I do is simple. So p of s will be split into odd and even powers. Q of s will be split into odd and even powers. Okay, then you take the multiplication of m1 of s into m2 of s minus n1 of s into n2 of s. Substitute s is equal to j omega. If after substitution of s is equal to j omega, if this product, okay, right, if it is greater than 0, then the third condition is satisfied. If it is less than 0, then this condition is said to be failed. Okay, so right, the actual condition is the real part of h of j omega should be greater than 0 when for every s is equal to j omega. Okay, for every value of s is equal to j omega, we should get this condition. Okay, but this is very difficult to test. So what we do is, we split the numerator and denominator into odd and even powers. m1 of s is even power, n1 of s is odd power of p of s. m2 of s is the even power of q of s, n2 of s is the odd power of q of s. Okay, after splitting, then what I do is, I get the product m1 of s into m2 of s minus n1 of s into n2 of s. If I take this, right, and substitute s is equal to j omega, then, right, if this is greater than 0 after substitution of s is equal to j omega, if this value is a positive value, then the third condition is satisfied, which is a very important condition of the three. Okay, so if this condition is satisfied, we call, right, the network function as a positive real function. Okay, so right, if a network function satisfies these three conditions, it will be called as a positive real function. Okay, right. Okay, so first condition is the denominator polynomial, which is q of s, must be a Hurwitz polynomial. Second is, right, the value of h of s should be real for all the real values of s, which will be checked by checking all the coefficients. If all the coefficients of the numerator and denominator are positive, then we can satisfy the second condition. Okay. The third condition is the real part of h of j omega should be greater than 0 whenever s is equal to, for every s value which is equal to j omega. Okay. So to test this, so the condition that we need to check is m1 of s into m2 of s minus n1 of s into n2 of s at s is equal to j omega should be greater than 0. Okay, so right, these are the three conditions for testing whether the network function is a positive real function or not. These are also called as the properties of the network positive real function. Okay, so right, whenever if we want to do synthesis, right, we have to first test whether the given network function is a positive real function or not. Without testing, right, we cannot do the synthesis. Okay, so only positive real functions can be synthesized. Okay, right, so that is it for this lecture. Thank you. In the next lecture we will see how with the help of an example, one or two examples, we will see how we can verify or test the network function is positive real or not. Okay, right. Thank you.